Hi everybody. Today I'm gonna present a paper from Dr. Patrick Kopic, our professor, and Dr. James Ken from Emory University. So the paper is about determination of phase transition temperatures for atomistic model of lipid from temperature-dependent stripe to macrokinetics. So many lipid bilayers undergo a reversible order disorders transition between the gel and liquid crystalline LC phases at the main phase transition temperature Tm. And Tm is an important characteristic property for the lipid. And what is the LC phase? Is the liquid crystalline phase, and this is the distinct phase of matter observed between the crystallized solid and isotropic liquid state. There are many types of liquid crystal state depending on the amount of order in the material. And it has three types. They are nematic, smectic, and columnar. This report describes an approach to evaluating Tm within the molecular simulation of a lipid bilayer based on the strategy of isolating the fast growth state, and that is the step 2 in the LC transition. This simple method consists of preparing a system consisting of gel and fluid phase coexisting in adjacent stripes and observing the rate at which one phase or the other grows as a function of temperature. The figure 1 is the two-phase system construction before and after equilibration. The A, B, and C is the lipid in DBBC system, and the D is in the SBC system, and the one on the left is before equilibration, and the one on the right is after. So the pre-equilibrated gel was incubated with half of the lipid set at 293 Kelvin and the other half, and the solvent set at 353 Kelvin for 10 nanoseconds. And the stripe in that is for DBBC system, and the stripe that the SBC system were constructed similar to DBBC, except that the gel and the LC solvent will run at 303 and 363 K respectively. And all the molecular dynamics simulation will run with Chromax 3.3 and 3.4. The table 1 is the description. The range temperature for each lipid system was simulated as the different temperature. And the figures 2 is the DSBC tail order versus the temperature. And re-equilibrated DSBC LC cool at a different rates. So is the time evolution of fraction of tail dihedral in the strand conformation for simulation run at 1.5, 0.2, and 0.1 Kelvin per nanosecond. In principle, a radially cool lipid bilayer should undergo a phase transition at the characteristic temperature Tm. At least two previous simulation studies have aimed to determine Tm through this approach, but in both cases, a re-equilibrated LC system would cool at 2.5 Kelvin per nanosecond. The SPC will cool from 333 Kelvin, 5 Kelvin above the experimental Tm at even slower rates, 1.5, 0.2, and 0.1 Kelvin per nanosecond. The fraction of azotyl strand dihydro initially increased slowly with decreasing temperature. So it's increasing slowly with the decreasing of the temperature. The two-phase simulation of both DBBC and DSBC run at several temperatures. Is shown in Table 1 that the speed and direction of the phase transition change with temperature. And we can see in the figure 3 and figure 3 and figure 4. It's figure 4. The DSBC simulation at 3 this is the DBBC system and this is the DSBC system. The DSBC simulation at 313 Kelvin, for example, is exhibit the visible widening of the gel stripe, while the highest temperature is 328 and 333 Kelvin. The gel is blandly melting at the interface. This is the 313 Kelvin. This is the 333 and 328. At the intermediate temperature, the strain is not immediately obvious. So it's kind of like similar strain as the lowest temperature. By cross-qualitative measures, the two-phase method appeared to indicate a Tm between 313 and 328 Kelvin for the DSBC model, a range beginning 15 K below experimental and extending up to the Tm. And for at all temperature, the change in lipid order will localize at the gel fluid interface, even for the DBBC at 313 Kelvin, whereas the gel phase melted completely. Melting occur from the battery inward. This observation is consistent with the notion that phase nucleation is the rate-limiting step. This is the DSBC two-phase system, the snapshot of that. And we can see at the At the 328 Kelvin and 333 Kelvin, the lipid begins to melt. And we can tell that at the 333 Kelvin, the lipid they melt completely. The figure 5 is the gel LC interface below the main transition temperature Tm. The lyserol backbone and ASO12 of the SPC system simulated at 313 Kelvin at T at 0 nanosecond and 100 nanosecond. These figures reveal that the lipids that have transitioned from a LC to a gel at the interface exhibit decreased lateral orientational order relative to those in the repair gel stripe. The snapshot at down the tail primary axis to highlight the arrangement in the hexagonal array. Although the tail still form an hexagonal array tilted parallel to the stripe dimension, the two tails of the given lipid may not lie in the same row and may not even occupy nearest neighbor site within the hexagonal lattice. The figure 6 is the plot between the mass phase increasing rate versus the temperature. The red one is in the BBC system and the green is the SPC system. We can see as the temperature increase, the rate of gel curl decrease for both the SPC and the SPB system. And this figures is the rates of main simulation of DBBC compared with the DBBC control. This is the quantitative measurement of domain growth, the average rate of expansion and retraction of the gel phase H for DBBC and DSBC at its temperature was estimated by linear regression from the data from figure 3 and the plot in figure 6. In And the equation for the rate is like this. This equation makes phenomenological sense if considered the conversion between the phase to be an activated process with activation energy EA and a driving force proportional to the difference in free energy between the phase and proportional to Tm. Tm minus T and is close to the transition temperature. Apparent activation energy is 70 kJ per mole in both systems. The transition temperature calculated from fit to this equation is 308 Kelvin for DBBC and 323 Kelvin for DSBC, and they are closer to their experimental transition temperature than the previous study have suggested. Other scientists estimated that the Tm of DBBC using this force field to be 10 K less than experimental Tm, and the Tm of the DSBC to be 29 K less than the experimental Tm. This study suggests that the simulations model may underestimate the Tm by as little as 6K for DBBC and 5K for DSBC. And this study was to estimate the Tm. So the actual value of the rate of domain curl is also interesting. An experimental study indirectly established that within 5K of Tm in DBBC, the interface travel at the rate proportional to T minus Tm, with a constant equaling 0.002 nanometer per nanosecond Kelvin. A coarse-grained model study reported linear dependence of domain curl with a slightly higher coefficient, 0.007 nanometer per nanosecond Kelvin. This table too. The stripe curl method use a higher Tm than annealing method lies in the stability of the gel phase. The stripe growth method is itself subject to several potential sources of error in calculating Tm. It replaces the uncertainty of generating the gel phase through quenching with uncertainty associated with initial construction of the alternating stripe structure. For the gel phase domain in particular, choice of an initial configuration may bias the gel structure even over the course of a 100 nanosecond simulation. In an attempt to control for the effect of how the initial interface is prepared, stripe systems were prepared in two different ways. First, by melting half of the lipid in pre-equilibrated gel, and then by flanking pre-equilibrated gel with pre-equilibrated LC. It's in figure 1. For the conclusion, the determination of the main phase transition temperature of lipid bilayer simulated with atomistic force fields is an important step in force field validation. The rate of phase growth in coexistent gel and LC phases reform into stripes have been investigated as the new way of obtaining the main phase transition temperature Tm. And the results from this study indicate Tm values that are higher and in closer agreement with experiment than those obtained through annealing study. The use of linear phase interface allows the measurement of rate of the macro, yielding an estimated activation period of 70 kJ per mole per the transition, with absolute rate of the same order of magnitude as those determined by experiment. Whether this disorder is localized at the interface and act as a barrier to further growth, or such disorder is in fact more characteristic of pool gel state than the order structure originally prepared remain a question for future study. That is on my presentation. Thank you for listening. Have a good night.